Hello, everyone. It's okay. Last week, or well, the last time we met, we talked about um the geodesic equations. Um, and we introduced them as, like distance minimizing curves, and then we found that such curves must obey, well, the geodesic equation. And we saw that the geodesic equation, um, intrinsic, like it depends on the choice of metric, which should be obvious. Um, so yeah, it gives us now like the metric now gives us ways of measuring distances. Um, and so on an arbitrary manifold, like there's no canonical way to define distances since it's not embedded in Rn a priori. So the Riemannian metric gives us a way to do this. Um, it was actually, I think, proposed by Hilbert, not Hilbert, sorry, Riemann, um, that geometry be done using the metric and not really the underlying topological space, because somehow the topological space is different from the metric structure you put on it. As we saw, there's no canonical choice of metric. So again, um, there should be no reason why, the topology and like the metric or the way you measure distances coincide in any natural way. But it turns out that if you give a metric and then you define distances the way we did last time, the topologies do coincide, right? So, I mean, again, that should make sense because the open sets are now given by, measuring distances and stuff like that. But okay, that all being said, I want to like carry on I want to present the ideas that Riemann had, or at least one of them. And that's the idea of Riemann normal coordinates. So today at least for the beginning, we'll talk about Riemann normal coordinates. So what exactly do these coordinates achieve, right? So we are looking for Riemann normal coordinates. Okay. So what exactly do Riemann normal coordinates do? So the idea is that the Christoffels are somewhat ugly, right? If you remember, um, the Christoffel symbols were defined using something like this. And now the idea with Riemann normal coordinates is we want to find they're the coordinate system in which these Christoffel symbols vanish. Um, in Riemann normal coordinates, these vanish. Okay, that's wonderful. But now, how do we even find such coordinates? Right? How do we even find such coordinates? Yeah, so how do we even find such coordinates? And the method we're going to use is we're going to start actually first going to define an exponential map, similar to what we did when we talked about Lie groups. So, let's first start talking about the exponential map, and then we'll see how the exponential map will allow us to define Riemann normal coordinates in a very natural way. So, let's recall the geodesic equations. So, if U phi is a coordinate system, is a chart on M. Then the geodesic equation um, may be written as, so it's x double dot k plus kij x dot I x dot j equals 0. Okay. But now this is just a system of ODEs, right? This is a system of ODEs. And since it's a system of ODEs, as we talked about last time, we have unique solutions given initial value. So we have existence of a geodesic through a point P and M with with initial velocity xp. Right? We do have the existence of such a geodesic. But now, in the case of Lie groups, the exponential map was easier to define because if you recall, we defined it to be the time one flow um, of this geodesic. Sorry. We defined it to be the time one flow of this vector field. But in this case, we don't have such luxuries, right? Um, and so what we're gonna do is we're gonna just define it on the subset of TPM, um, where the time one flow does exist. Okay, so we define. So now the exponential map is a map from some open subset in TPM. You can check as an exercise that it'll be on some open set of TPM. Um, Again, this follows from like facts, like the usual facts of ODEs. So now we're going to define the exponential map at P, V, to be gamma of 1, where gamma is the geodesic um, through P uh, with velocity V. And note that, XP is only defined on, a priori on some open subset. Um, is only defined on some open subset of TPM. And here we're giving the uh, topology given by GAP. Right? So I mean, it's okay. It doesn't like give you an exponential map on the entire space, but it gives it to you on some open subset. Um, a lot of the times we'll be working with compact manifolds, in which case time one flow always exists because every vector field is complete. Um, and since every vector field, since every ODE has um, solutions for all time, uh, this issue doesn't even arise. So it's not too bad. And then we can, extend this. We now have a fiber-wise map on the tangent bundle, technically on some like sub-bundle of the tangent bundle, and then you define the exponential map throughout similarly. Okay, so let's just do a basic fact about the exponential map, and that's for any p and m. We have that the derivative of the exponential um the exponential map at P at the origin is simply equal to the identity map on the tangent bundle. And here we're identifying the tangent space at the origin of the tangent space of this with just TPM. Because remember, this is a vector space, so its tangent spaces are canonically identified with the space itself. Proof. The proof is very simple. So let x, let x be in TPM. Then d of the exponential with p at 0 of x is equal to d by dt t equals 0 of the exponential of dx, which equals d by dt t equals 0, gamma tx. But then this is just gamma of 0, which is 6. Okay, very good. Okay, with this lemma out of the way, this now shows that, um, this now shows that TPM is a local diffeomorphism, is a local diffeomorphism um, around 0 with some open subset containing P. Okay, that's wonderful. Why does this help, right? Well, we'll see in a second why this helps. So again, all we've done is we've defined a way of moving along geodesics. That's the idea. So in these coordinates, or we haven't defined any coordinates, but intuitively, if you were to move along a geodesic, that would be equivalent to you moving in the direction x and just, staying in that direction. So intuitively, you would be, moving in a straight line. And we'll see shortly that the geodesics in this coordinate frame are, sorry, in the coordinates the exponential map define are precisely straight lines. Um, but before we get there, let's do one side quest. So with this, um, let the metric be given by, some local expression, as always. Um, this is around P. Then what we can do is, these note that the GIJs are functions, are real valued functions um, on some open subset. So what we can do is we can find the Taylor expansion. So we can find, well, it's technically the Taylor expansion. Um, so technically, GIJs come from Rn, and what they do is they first map you, they go into the open subset, and then they you give it the usual coordinate frame, the coordinate basis, and then it gives you whatever. So what we can do is we can now Taylor expand this around the point P. So, you get Gij at the point P plus partial Gij partial xk at P uh, xk plus 1/2 partial Gij partial xk partial Gij partial xl xk xl, and then, higher order terms. But we don't really care about the higher order terms. We just want that we want. So if the Christoffel symbols are to vanish at the point P, right? If the Christoffel symbols are to vanish at the point P, this is equivalent to both this and this vanishing at the point. Oh, sorry, not vanishing, but this being constant and this being 0 at the point P. So we want Gij to be delta ij and partial Gij at, this to be 0. And all of this is at the point P, specifically at the point P. Um, okay. We can, we can be a little sloppy and write it like this. Okay. Now, what we're going to do is we're going to use the fact that, the exponential map is, um, is a diffeomorphism. So what we're going to do is we're going to treat an even smaller subset of this open set. Um, and then we're going to take some part of the tangent space and we're going to say, okay, the tangent space at this point will roughly approximate some open subset containing P. That's the idea that we want to use, right? That's why we defined the exponential map, because what we're basically saying is that, okay, globally this surface might be curved, but the tangent space is like flat, right? Since the tangent space is flat, some open subset of the tangent space will also roughly be flat. And then you just, push that onto the set and say, okay, this is like roughly flat. So it's flat up to like, as we'll see, it's actually flat up to second order. And then the deviations that you get will be called the curvature, um, which I'll give you some readings because the proof is quite involved. Um, so I'll give you some readings um, based on this. Um, it's given in I don't know if you can see this, but it's given in it's a comprehensive introduction to differential geometry, part two by Michael Spivak. Um, and the proof is, given in like the outline. Sorry, not in the outline. He goes over like Riemann's original work and then, talks about how Riemann came up with it and stuff like that. So I'll, give that as a reading. But okay, with that being said, let V be some open subset, be an open subset of TPM, open subset, such that um, the exponential is diffeomorphic, is a diffeomorphism. Um, and you know, actually this condition is not really that important. So it's a diffeomorphism. So now what you do is actually, let's put it. And the image of the exponential is contained within U. So we just have to, if anything, we'll have to like constrict um, V a little bit, but that's not really that bad. Let x1 up to xn be an orthonormal basis. Be an orthonormal basis of TPM. Um, Hence, we get an isomorphism TPM into Rn. Let's call this E. And E at, AIXI is just equal to A1 up to, say, AIXI is just A1 up to A. Okay. But now since this is an isomorphism, then um, phi equal, have we used phi before? Yes, I have. Okay, let's call this psi. Psi equal E compose the exponential inverse P is a chart. Um, is a chart on V hat, which is the image. Okay. And why is this a chart? Well, it's, clearly it's, uh, you know, clearly we can take the derivative. Clearly this thing is smooth because the exponential is smooth. E is smooth. Um, Moreover, if I take d psi at the point P, well, rather d psi inverse at the point P, then this is just equal to d of the exponential of P composed with d E inverse. and this will be at the point 0. Um, and this is just E inverse, right? So what this means, um, hence, the coordinate vector field is equal to d psi inverse at P dxi at 0. Oh, before that also note that psi p is equal to e of the exponential inverse at P of P, but this is just e at 0, just at 0. And this equals E inverse of xi at 0. And then this is clearly just xi. So what this tells you is that the coordinate frame is an orthonormal basis. Is an orthonormal basis of TPM. Okay. But now why is this good? This is good because if I take G IP, which is just the inner product of GXI at P, GXJ at P, this is just 0. That's right. This is just delta IJ, right? Because um, the coordinate frame is an orthonormal basis. Okay. That being said, we still have to show one thing. I was initially going to leave it as an exercise, um, but I think we'll show it because it is slightly confusing as to why it must be true. Um, hmm. Actually, we don't care about that. I'll leave it as an exercise. Um, I'll leave it as an exercise, and then we can um, I'll outline the proof in the problem sheet. Okay. Um, Now note that um, exponential composed C is a geodesic um, centered at P, or starting at P, starting at P with initial velocity um, x v equals c I x I, right? Since you're composing a geodesic on Rn with the exponential map, which gives you the geodesics. So if you take the differential, it's just the geodesic equation on Rn, which is a 0 because C is a straight line. Um, what this means is that the geodesic equation, okay, so hence for geodesics in this frame, in this coordinate, in these coordinates, for geodesics in these coordinates, x double dot of k is equal to 0. Hence, um, the geodesic equation reduces to gamma jk partial xi partial xj equals 0 for any initial conditions. this tells you that at this point there must be zero. This is at P. Okay. So in Riemann coordinates, it's nice that the Christoffel symbols vanish. Um, and then so it's good to have a coordinate system in which the Christoffel symbols vanish. We'll see later on that the Christoffel symbols will play like an important role when we start talking about, taking derivatives in the direction of vector fields, because that's sort of the idea that that's sort of how we defined the definition of a vector field, right? We want it to be able to move in a certain direction and then um, find what the derivative of a function is moving in that direction. And that's sort of the idea that we'll now generalize, right? We'll so let's now talk about that, right? So the idea is we want to define something that'll allow us to, take the derivative of something in the direction of something else. So what we're going to do is we're going to define uh, this nabla symbol to be, it'll take in a pair of vector fields, right? And it'll give you another vector field out such that it is it is bilinear over R, um, and such that one, what it does is if I take nabla of fx plus gy and z, this is f of nabla x z plus g nabla y z, where f and g are smooth functions on M. Second, if I take x f y, I should get x f of y plus f of nabla x y. Right? And this second condition is sort of like the Leibniz rule that we want, right? This is very similar to what the Leibniz rule looks like. What we're gonna do is we're gonna, instead of writing x, y like this, what we're gonna do is we're gonna just, you know, simplify the notation a little bit to make it look nicer. Um, and then this also sort of looks more like the usual definition of the directional derivative that we used to. Okay. But note that, okay, in this definition, there's nothing special about the tangent bundle, right? Like we took sections of the tangent bundle, we differentiated them along some vector field, and we got another section of the tangent bundle. There's nothing special about the tangent bundle. So what we're going to do is like if we have some arbitrary vector bundle, we can similarly define a map that does both of these things. Um, and we can just do that. So let phi e m be a vector bundle, then we can define a map that takes, we take some vector field to differentiate in the direction of, we take some um we take some section to differentiate, and that gives us a new section, right? Similarly as above. Okay, we'll call maps like this connections. Okay, so maps like these will be called connections. Now, since we've defined this on some like arbitrary vector bundle, um, a natural question would be, is there is there a canonical way to extend like if I have a connection on some vector bundle, is there a natural connection that exists on all its tensor bundles that only depend on the definition of, what the vector bundle does. Sorry, what the connection does on our chosen vector bundle, right? Um, and the idea, I mean, and the answer is yes. So if nabla is a connection on, this, then nabla extends um to a vector, sorry, to a connection on each tensor bundle, such that it commutes with taking the trace. So what I mean by that is if I take trace of f, this will be the same thing as taking the first applying the connection and then taking the trace. And it gives you a Leibniz rule on taking tensor products. Right? So that tensor G plus F tensor knob X. Right? So both of these conditions make sense. Um, okay, that being said, let's okay. So now that we have the definition of connection, let's take a step back and let's stick with the theme of generalizing objects that we've already defined. Um, and the easiest thing to generalize as well, the Riemannian metric. So instead of the Riemannian metric giving you distances only on the tangent bundle, we can ask, okay, can I define a Riemannian metric type object on any vector bundle? Because I can take, I can take inner products on each, because for a vector bundle, the fibers are vector spaces, and I can define inner products in each of these fiber spaces. Sorry, on the fibers of this space. So I can define a Riemannian metric on a vector bundle very similarly to how I did for the tangent bundle. So let pi eta m be a vector bundle. Then, we take a section of the symmetric bundle of E that is positive definite and non-degenerate on each fiber. Right? Then we call E M pi G a Riemannian vector bundle. Okay. That's enough of this. Let's now see like why Christoffel symbols are so nice. Okay. So remember, locally, the Christoffel symbols were just n cubed functions that happened to pop out of a choice of metric. But there's nothing special about those metric, like about those functions, right? We could have chosen any arbitrary, um, we could have chosen any arbitrary n cubed functions, um, and then ask the question, is there a metric whose Christoffel symbols are these functions? And the answer to that question is like, it depends, right? If we just happen to choose the correct n cubed functions for the given choice of metric, like you would already get the Christ like then yeah, then the answer would be yes. But the Christoffel symbols also have some internal symmetries to them, right? Um, like for example, they're symmetric in the bottom indices, right? Um, and so in general, the answer is no, but in the special case, it is. It's very good. Um, okay. So let Mg be a Riemannian manifold. And usually when I say Riemannian manifold, I'll mean a Riemannian metric on the like tangent bundle. We get, Christoffel symbols as above. I don't wanna, I'm not gonna, whatever. We get as above, right? What we can now do is ask ourselves, okay, do these form a tensor on our space? And the answer is no, they don't form a tensor. And it's an exercise to check why they don't. Um, my hint is if I do a chain of coordinates, these don't transform the way we would want tensors to transform. Um, however, we can define a connection out of these. So let partial I be the let partial I be the coordinate frame. Define partial I, partial j as k I j partial k. Okay. And then you can check now that I can define a connection on the on um I can define a connection on all of TM. But then now you have to be careful. You have to make sure that it satisfies um that it agrees on overlaps and so on and so forth. So um be very careful. Um we might check this next time. Actually, yeah, let's do that. So define this. Um so next time we will show that this defines a connection on TM. But for now, let's just see what properties this connection has. First, let's see what its extension is to the cotangent bundle. Because once we have that, we can just take tensor products and see what happens. But okay, so to do that, let dxi be the dual to partial I. Then dxi partial j is nothing but the trace of dxi with partial j. And this thing also equals delta ij. Okay. Um, which then means that if I take actually one thing I forgot to define here is such that this and partial xf equals xf for um, functions for f in C infinity m. And this is a condition for if um, E equals the tangent model. Yeah. Okay. So now if I take, if I take if I try to find the connection um at at this thing, what I get is this is zero because it is equal to the connection of the trace of a constant function. And this is equal to x of delta ij, which is nothing but the trace of the connection, sorry, which is nothing but the connection on the trace of dxi with partial j. And as we know, these commute. So this is the trace of this. And then this is nothing but dxi, which is what we want to find. Um, and excuse me, um, and dxi tensor x partial j. Okay. And this is just equal to dxi evaluated at partial j plus dxi evaluated at this. Okay. Which now tells me that the connection applied to dxi at the point at this coordinate vector field is negative dxi applied to the connection of the coordinate. So if we want to find, okay, so now this thing equals alpha I, sorry, alpha I downstairs dxi. Um, sorry, this equals, sorry. So this, so this is a one form, right, on M, which means that it has components alpha I, let's do alpha j, dx, hmm, let's do ij dxj. So if I apply this at, say, partial k, what I should get is ij dxj partial k, and this just equals alpha I k. Okay. With this out of the way, we can now, we can put things in here to find what these components should be, because as we saw below, this is nothing but alpha ij. So if we set, so if partial j equals x, so if partial k equals x, then we get in this direction, um, xi alpha j is nothing but negative dxi partial k partial j. But if we look carefully, this is just given by the Christoffel symbols, right? This is nothing but alpha kj partial alpha. And then this simplifies to I k j. So finally, if x is equal to xi partial I, we get that the connection applied to dxi is simply, well, it's simply, partial xi dxi, which is bilinearity, um, just this, which is nothing but negative this I j k dx. Okay, with this out of the way, we can now um, compute compute what the connection would be along some direction x on the metric tensor itself. So in these coordinates, we get the following expression. dxi tensor dxj. Here we're not using the symmetric product, so we need to make sure to keep the factor of 1/2. And this equals 1/2 partial gxij partial dxi tensor dxj plus gij partial x di plus, yeah. And now just, plugging things in, this gives you 1/2 xk partial k gij dxi tensor dxj plus um well, negative gij. Okay, sorry about that. I don't know what happened there. Um, this just gives you gij x alpha gamma I alpha k dxk tensor dxj minus g ij x alpha gamma j alpha k dx I tensor dx k. Okay. Now what we're going to do is we're going to look at this term and we're going to realize that we're just going to swap I with k. And the reason we can do this is because we're summing over i's and k's. So, and they're just indices, right? Since we're summing over all the indices, it doesn't matter what we call the index. So we're just going to make that swap. And we're also just going to swap k with the j on this side. Okay. What that gives us is the following. Um, so also we're just going to call k alpha just to be consistent. So we can pull out an x to the alpha and we're going to get partial alpha gij minus gjk gamma k alpha I minus gik gamma k alpha j dxi tensor dxj. Okay. Now, all we have to do is we'll just expand this, like these Christoffel symbols. We'll just expand them and try to see what happens. I get this minus. Okay. Now, note that this term, and this term are all the same. But now we have minus signs here, here, and halves. So this, and this cancel out. Similarly, so with this cancel out. Similarly, this term cancels out this term, and this term cancels out this term. So what we're left with is that it's 0. Okay. So what this means sort of is that in some sense, the metric tensor is constant. Okay. Um, in some sense, it's constant if we move in any direction. which is kind of trippy to think about. But we'll see that, this property of a connection is very important, especially when we're doing physics. Um, so this property is called metric compatibility. So um, yeah, so this property is called metric compatibility. Um, and as we've seen, any metric has a metric compatible connection given by its Christoffel symbols, right? So given by the Christoffel symbols, it actually turns out that for uniqueness we need one more property, and that's known as torsion. Um, but we'll define torsion next week, or sorry, next time. Um, so an aside, I'll just put here. Every Riemannian manifold admits a unique torsion-free um, metric compatible connection called the Levi-Civita connection. And the proof will follow like basically immediately once we define what a connection is. I sorry, what torsion is. Anyways, if F is a section of E and or sorry, if 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 this equals 0 for all x, we say F is flat or F or parallel. And in some sense, this just means that, like, it doesn't really change when we move along it. Um, Now the parallel nature of the metric has, an important consequence, and let's see what that is. So let's say we wanted to take the inner product of two vector fields, and we wanted to see, okay, if we move in some direction, how does this inner product change? We know um, in usual calculus, taking the inner product is bilinear, and since it's bilinear, it follows product rule. Now, the question now is, okay, does this hold when we talk about um like connections as well? And in general, the answer is no, because the metric might not be compatible with the connection. But if the metric is compatible, then we do have a product rule for taking inner products. So let's see why this is true. So um corollary. So if A, B are, vector fields, then the inner product of A and B is equal to 0. No, well, in the connection. Uh, and proof. Note that this is the trace of G with G tensor A tensor B, right? So let's just apply the connection. Since it commutes with the trace, we get that this is the trace of the connection applied to G tensor A tensor B, which is just the trace of the connection applied to this A tensor B plus G tensor A tensor B, G tensor A tensor nabla X B Okay, but now the first term is a zero. This is a zero. So we're left with the trace of G tensor. I'm just gonna copy. Just gonna yoink that. And now this is just G of nabla x a b plus G of a nabla x b. Okay, so in this sense, we have like some, product rule that holds for metric compatible connections. One final thing that I want to define, right, is given a connection. So given a connection, given a connection, um, now we can define. So we can sort of look at this differently, right? Um, we can define the connection of a section to be something that takes in a vector field and then gives me another section, right? So we can define a map that I'll call gamma hat that takes in a section, right? And then, so it takes in a, yeah, it takes in a section. And what it gives me is it gives me the section of the bundle where I take in a vector field and it gives me another section. So since I take in a vector field, it has to be, part of the cotangent bundle. And then um, I have to tensor the vector bundle itself. So let's, make sure that this makes sense because this is a um, very important notion. So if you recall, this bundle, um, this bundle can be thought of as the space, can be thought of as the bundle whose fibers are maps, uh, TPM into E. Okay. So that's the idea with this. So what we're gonna do is we're gonna define this on a bun on a section F. It takes in um so that if I give it a vector field X, it just gives me the usual connection. Okay. With this, now what I can do is I can do something kind of cool, and I can define, you know, taking the connection of the connection of the connection and so on and so forth. Um, but I will outline that in the problem sheet for this week. But okay, um, if there are any questions, please let me know. Um, and I will see you guys on Friday. Oh, sorry, Saturday. Um, let's just delete this page. Okay, bye-bye.